Hello, today our group will be exploring some key concepts of electricity. To begin with, I will be creating a simulation and describe along with the creation. To begin, I will be adding a battery to our circuit, which will provide an voltage, or known as potential difference. It is an energy required to move a unit charge between 2 points in the circuit. It is measured in volt and calculated using the formula V equal W O Q, where work done in joules, charge in coulomb. And essentially, voltage acts like the pressure that drives current to a circuit, ensuring energy flow efficiently. Next, I will be adding a wire to connect it to the circuit. In real life, the wire will provide some resistance, but in this case, it's not the main resistance. The main resistance will come from the resistor. The resistance is the opposite of the flow of current. It will act like a friction in a water pipes. It's measured in ohms and depend on factors such as the material and length, thickness of the conductor. For example, copper has low resistance, making it an ideal material for wire, while longer wire tend to increase resistance. And next, I'll be adding our output, which is an light bulb, and connecting it with a wire. After I've connected the circuit, I have fully connected. You can see an electron moving through the circuit. It is also known as a current. Current is the flow of electric charge to a conductor, similar to water flowing through a pipe. It's measured in amps and is calculated to the equation I equal QOT, where current in amps, charge in coulomb, and time in second. For example, 12 coulomb of charge flow in 3 seconds. The current will be 4 amps. This simple equation highlights the direct relationship between the charge, flow, and time. It is also fundamental to powering all electrical devices. Without current, the circuit would remain inactive. And next would be Ohm's law. Ohm's law states that the voltage across resistor is directly proportional to the current flowing through it, with resistance as the constant of proportionality. For example, if a resistor has a resistance of 5 ohms and the current is 3 amps, I mean, the voltage would be 15 volts. Ohm's law is crucial for designing circuit and ensuring they operate safely and efficiently. As you can see in the simulation, V is equal IR. If I increase the voltage, the current will increase, but if I decrease the voltage, the current will decrease. It's a direct proportional, but if I increase the resistance, the current will decrease, but if I decrease the resistance, the current will increase. It's an indirect proportional.
Next, we're going to talk about the ammeter. The ammeter is used to measure the electric current, which is the flow of electric charge in a circuit. Current is measured in ampere, and it's defined as the rate at which charge flows through a point in the circuit. To measure the current, the ammeter must be connected in a series with the component, ensuring it measures the full charge flow through that branch. Importantly, an ammeter has very low resistance, so it doesn't affect the current it's measuring. So as you can see in the simulator, this is a ammeter, and as you can see, it can measure in 0.9 ampere throughout the circuit. And the reason why throughout the circuit the current is equal at 0.9 ampere is because the conservation of charge, which I will later explain in the video. And let's move on to the voltmeter. A voltmeter measures the voltage or the potential difference between 2 points in a circuit. Voltage tells us how much work done per unit charge to move a charge between those points, and it is expressed as V equal W over Q. And V is representing the voltage in volt, W is the work done in joules, and Q is the charge in coulomb. These equations tell us that a high voltage means more energy is transferred per unit charge. For example, a 12 battery does 12 joules of work to move 1 coulomb of charge throughout the circuit. Also, a voltmeter is connected in a parallel to the component or point being measured. It has a high resistance to prevent significant current from flowing through it, ensuring an accurate measurement. And a voltmeter measures the potential difference between 2 points in the circuit. Whether it shows a positive or negative number depends on how the probes are connected. And as you can see here, when I put here, it shows 9 volt. And if I swap the red to measure it on the left hand, it shows as a negative number, which is minus 9 volt. And this is because the polarity of the probe. The red probe is typically the positive terminal. The black probe is negative terminal or ground. If the red probe is connected to a point with a higher potential than the black probe, like this, if the red probe is connected to a point with a lower potential like this, it will show a negative number. But if the red probe connected to the higher potential, it will show a positive number. So now let's move on to the conservation law in the circuit, which the electric circuit need to obey 2 key conservation law. The first one is conservation of charge, which said that the total charge entering a junction in a circuit is equal to the total charge leaving the junction. This ensures there is no loss or accumulation of charge. Another one is the conservation of energy. The total energy supplied by sources like battery in a closed loop is equal to the total energy used by the component like resistor. This means the energy provided to the charges is fully distributed among the component in this circuit, ensuring no energy is lost in an ideal circuit. Bringing it all together, imagine a simple circuit with a battery, a resistor, an ammeter, and voltmeter. The battery supply energy to creating the potential difference, as you can see. The ammeter measures the current as charge flow, which is 0.9 ampere, as you can see here in the simulator. And the voltmeter is like this. If you put the red probe at the higher potential difference, you can see it shows a voltage which is 9 volt in the simulator. And conservation law ensures that the energy and the charge in this system are balanced. Charges entering the resistor equal those leaving, and the energy supplied by the battery is equal to the energy dissipated as heat in the resistor. Next up is the formula to calculate the power in a circuit. So there are 3 ways to write this formula. The first one is P equals IV. So in this case, I is 3 and V is 9. So the power will be 27 watts. But another way to write the equation is by substituting V to be equal to IR. And now the formula will be P equals I squared times R. And the last way to write the formula is by changing I to become V over R instead. And so the formula will become P equals V squared divided by R. And then the next thing is resistivity. So this changes depending on the material. Something like wood will have really high resistivity, while something like copper will have really low resistivity. So the formula is resistance is equal to the resistivity multiplied by the length and then divided by the cross-sectional area. Next up is the properties of series and parallel circuits. So in a series circuit, the current always remains the same. It's always 3 amps, no matter where it is in the circuit. However, in a series circuit, the voltage will be divided between resistors. So the total voltage is 9. This resistor has 1 ohm resistance, so V equals IR, and 3 times 1 equals 3, so the voltage is 3. While this resistor has 2 ohms, so 3 times 2 is equal to 6 volts. And the whole thing added up will add back up to 9 volts. But as you can see, it gets shared between the resistors. On the other hand, in a parallel circuit, now this is parallel, the current is no longer the same. Now changes depending on where you put it. However, the voltage is actually the same everywhere in a parallel circuit. It's always 9 volts. So in a series circuit, it still gets shared between the resistors, but in parallel, it's always 9. Next up is the behavior of resistance in a series circuit. So change this back to a series circuit. Okay, so resistance in a series circuit is really simple. You just take each resistor and you add its resistances together. So this resistor is 1 ohm, while this one is 2 ohms. So added together, the total resistance will be 3 ohms. Really simple. However, for a parallel circuit, the formula changes. The formula is 1 over total resistance is equal to 1 over resistance 1 plus 1 over resistance 2, and so on and so forth. So basically, this means that the more you add resistances in parallel, the lower the total resistance will be. So as you can see, this branch right here has a total of 3 ohms of resistance. However, now that we've added another resistor over here, the total resistance of the entire circuit has actually dropped, because you can see that now some of the electrons are now taking the new route instead, this route of 2 ohms, which reduces the amount of traffic, you could say, in the original branch, which means that now the electrons can now move more freely because there's more pathways for the electrons to move, and so the resistance overall has gone down despite you adding more resistances. Next, I'll talk about the effect of temperature on resistance. So in a conductor, as temperature increases, resistance will also increase because there are more collisions between electrons and atoms if the temperature increases. However, in a semiconductor, resistance can actually decrease if you increase the temperature, because in a semiconductor, more charge carriers can become available if the temperature rises. Next, I'll talk about some components in a circuit. The first component is an ohmic conductor. So these are conductors that obey Ohm's law, meaning that the more voltage you apply to them, the more current you get, and it will be linearly proportional, so the graph will be a straight line. However, for non-ohmic conductors, it won't be directly proportional, and so if you plot the graph, it won't be a straight line. So next component is a filament bulb. So these bulbs have a resistance that can increase with temperature, and as resistance gets really high and the temperature gets really high, the bulbs will emit light. Next component is the thermistor. These have resistance that decreases as the temperature rises, and the function of thermistors is to sense the heat in a circuit. And the next component is the capacitor. So these are used to store charge. So as charge moves from a wire into a capacitor, it will get stored in there. And even if the battery dies or is removed, then the current will still run for a couple more seconds because of the charge stored in the capacitor. The final component I'll talk in this video is the diode, which allows for the current to move in one direction only. So a common diode is the LED, which is a light emitting diode. So these also limit the current to only flow in one direction, and they also emit light as well. And that's the end of this video of our overview of electrical concepts and basics. So thank you for watching.